today is the 16th. Alrighty, let's go through. Yes?
When is the lab due?
Sunday night. Any other questions? Okay. Homer, how you doing? Okay, I'm going to go through the tests. If you have something wrong, but your work is essentially correct, let me know. Possibly partial credit, and then I'll give you the outline for the final. All right, first one. Density function. For x, we have a wire from 0, 0 to 1, 2. And we want to find its mass. So the line integral that gives the mass is the integral of our density function over the arc length. Okay, that's a line integral. Everybody see this okay? Okay. The parameterization, if you use the parameterization, the natural one, t, 2t, where t is going to go from 0 to 1, then what you would do is take this line integral over the arc length and change it to an integral in terms of the parameter t. The mass in that case would equal the integral from 0 to 1. We would take our density function for x is equal to t, times the square root of dx dt, 1 squared, dy dt, this is the x, this is the y, dy dt, 2 squared, dt. And this would be the integral from 0 to 1, 4t, square root of 5, dt. And that will give us the mass of the wire. If we use a different parameterization, we get a different looking integral, but the outcome would be the same. And this is t going from 0 to pi over 2. And the outcome would be the same. You get this integral for x dx dt cosine squared, dy dt is 2 cosine, 5 cosine squares, the square root of 5 times a cosine, so you'd end up with 4 square root of 5 sine cosine dt. Yes, still on there? Now, find the mass. Take your pick. The line integrals are independent of parameterization. In other words, in any parameterization, as long as you start at the start point, end at the end point, and stay on the path, doesn't matter the parameterization that's used, do either this integral or that integral. It really doesn't matter. They're about the same. This probably is a tad easier. When you integrate this, you'll get 4 square root of 5 t squared over 2 from 0 to 1. That's 1/2 times 4. It's 2 square roots of 5. Okay? And that's the answer. Okay, any questions on those? Nice. 5 through 10. Given a conservative vector field, and you're given some points, we want to find a bunch of things. Let's just take a look at it. We're given P, Q, and we're given the field. So what the heck? All right, we should find a potential function. To find it's already stated that it's conservative. So to find the potential function, integrate the x component with respect to x. Wow, did we do this one or what? All right, well, whatever. Okay, integrate with respect to x, that gives you a constant with respect to y. Integrate the y component with respect to y to get xy. Reconcile the two by coming up with one function that has both characteristics. Okay, that's our potential function.
I had a question about this.
Yeah, go ahead.
The mastering, or the WebAssign problem that had us do this added a plus K on there, but that wasn't on the exam. Is both ways right?
Yes, yes. Actually, I would tend to go with this one more than that one. I mean, obviously, any constant added to it still has a partial with respect to x that's equal to y and a partial with, but I think this is more useful. That's a good question.
So is that plus K, whatever the constants, C in terms of y or C in terms of x would be?
Yeah, you could have a constant. That constant would be a constant like a number, 7, 8, 9. It wouldn't be an x or a y, though. That would be incorrect. But a constant like k, just plain, would be fine. That would be fine. That's interesting. That's a good point. 6, find a linear path parameterization. Well, this is y equals 2x. The obvious linear path parameterization would be t to t. T goes from 0 to 1. What about the integral for work? Under this path, the integral for work would be the integral from 0 to 1. Now, what you have to do is take the field and represent it in terms of t, y, x. Y is 2t, x is t, r prime, dt. So that's one of those down here. It looks like A, right after, it looks like A. Find the parabolic path. Well, y equals 2x squared. If you let x equal t, the y is 2t squared. And that again would go from 0 to 1. But now we're taking a parabolic path from P to Q. The work integral, 0 to 1. Now it's y, x, r prime. Get a different looking integral, but as we know, the results will be the same. Find the work done. Well, you've got all kinds of options here. You could evaluate any one of these two integrals to do it, but the easiest way is, since we have a potential function, find the difference in potential to find work. The work is equal to a potential function at the end minus potential at the beginning. 1, 2 is 2, 0, 0 is 0, 2 joules of work. Okay? Okay, 14 through 20. No, we can't do 14 through 20, 11 through 13. All right, given the vector field, y, x to z, find the curl, I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, m, n, p. Now, these little partial guys here are called differential operators in this context. Hey, Dan. Okay.
I can't believe I didn't bring water. I'm such an idiot.
Fairly sure. Okay. That's it.
If not, just probably in here somewhere. Okay. Alrighty. So, find the curl. Here's what we do. Cross this out, cross this out. Partial of 2z with respect to y, 0. Partial of x with respect to z, 0. Cross this out, cross this out. Partial of 2z with respect to x, partial of y with the partial of y with respect to z, 0. 0, 0. Okay. Cross this out, cross this out. Okay. Partial of x with respect to x is 1. Partial of y with respect to y is 1. 1 minus 1 is 0. Whoops. Okay. We have a curl that's identically 0. Therefore, we have a conservative vector field. Yes, the answer to 12 is yes. And its potential function, what we're going to do is integrate this one with respect to x, integrate this with respect to y, we'll get xy again, and this with respect to z to get z squared, and that'll do it. Okay. Xy plus z squared satisfies all the requirements, namely the partial with respect to x, partial with respect to y, and the partial with respect to z. Any questions on that?
You're just integrating each.
Yeah, I integrated each. This with respect to x, this with respect to y, this with respect to z. Okay? Okay, how we doing? Good.
The first one with respect to x, so n with respect to x, n with respect to y, and z with respect to
And p with respect to z. Yep. Yep. Yeah, this one would be with respect to x, y, plus a constant in terms of y's and z's. But, so that's x, y. This is x, y. So you have an x, y, and then you get the z squared from there. Okay, 14 through 20. We are moving along. 14 through 20. All right, we're given the field. Y2, non-conservative vector field that it is. Okay, and we're given a square. 0, 0, 1, 0, 1, 1, 0, 1. Oops, okay. Okay. All right, counterclockwise, find a double integral that gives you work with Green's theorem. That's the double integral. It's the partial of n with respect to x, 0, minus the partial of m with respect to y, 1, dy dx. The y's are going to go from bottom to top, x's from left to right. We end up with 0 to 1, 0 to 1, 0 to 1. We get negative 1 joules of work. Okay? So that's negative 1. All right, now we're going to do, all right, one length at a time, one edge at a time. So, first one, R1 of t. We're going from 0, 0 to 1, 0. It'll be t, 0, as t goes from 0 to 1. First piece of work is the integral, 0 to 1. y2, y2, okay, dot, r prime, 1, 0. You guys all right out there? Jeez. We do no work going on along the x-axis, okay? We have no work to be done here, okay? W, the second leg. We're moving up the square, 1. Now, this is t, okay, but we have to adjust it because our t is going from 1 to 2, so it's going to be t minus 1.
So if we had a 0 to 1 there, it would have been the same thing?
Yep, exactly. It would be fine. And you know what? You could make a decent case for saying that's easier that way, and I'd have to agree with you. But I'm doing it in sequential order, the way it's normally done, but not always. 1 to 2. Now, we have y2. y2. R prime. 0, 1. That's 1 to 2. That dot product is 2. That's 2t. That's 4 minus 2. That's 2 joules of work heading up the square. Let's go across the top. We go across the top. Now it's decreasing by 1, okay, on the x. So I'm going to have a negative 1t, but I have to make an adjustment. My t is going to go from 2 to 3. I've got a negative t. At 2, it's negative 2, but I have to start at 1, so it's negative 2 plus 3. The y is 1. Okay? So, third work. 2 to 3. y2. R prime. dt. 2 to 3. Negative 1. Opposite of t, negative t. Negative 3 plus 2, negative 1 joules of work. All right, how are we doing out there? You guys all right? No, what's wrong? You okay? All right. Everybody's okay? Ed, you all right? Barely? You just barely hanging in there? All right, I'm almost done, almost done. Fourth piece, coming down. Coming down the side. 0, negative t. T is going to go from 3 to 4. Let's start at 3. At 3, this is negative 3, but it has to start at 1. Okay? And to go from negative 3 to 1, I'm going to have to add 4 to it. The work, fourth piece, is the integral from 3 to 4. Okay. y2. y2. R prime. And that's a negative 2. Negative 2t. Negative 8 plus 6. A negative 2 joules of work. Coming down that side. Okay, so what do we get? When you add them up, you get 0 plus 2 plus negative 1 plus 2. You end up with negative 1 joules of work, which is what we had from Green's there. Okay? And that is that. All right, any questions on that? We're moving along. Whoa!
Back to 14 there really quick. So to find the argument, you take the partial of n with respect to x minus the partial of m with respect to y. Right?
That is correct.
All right.
You got it.
Trick us by putting the y in the x place.
I had to change. Well, you know, I didn't try to trick you though, but it turns out to be that way.
Kind of would have turned out to be 0 though if it was like an x there or something.
Yeah, I know. That's the thing. I had to make it so it didn't come out to 0. Okay, let's take a look at the final exam. Here we go. Wow. So on your final. This is what you have. First section. This is section 1 through 3. You have a conic section. Okay? Ellipse, or parabola, circle. I wouldn't even give you a hyperbola. Okay? And basically, the idea is, given this conic section, put it in standard form. And it depends now. It depends on if it's an ellipse, I'd ask for the center. Okay, I wouldn't even ask for the focus. I'd ask for find the center in semi-major axis.
But should we be given the ellipse, the parabola, or the circle?
I'll give you the equation, and you're going to have to put it in standard form, and then you have to answer a couple of questions. This is the way I had it on the test. It's very similar to the test. The thing to do for all these is to look at your hour exams, the tests, that pertain to these topics that I'm going to give you. Now, on conic sections, there was a few of them. But I'm telling you right now, it's going to be the ellipse, parabola, or circle. And what you're going to have to do is put it in the standard form and then answer a couple of questions. If it's an ellipse, I'll ask for the center, semi-major axis. If it's a parabola, I'd ask for a vertex, concavity, opens up, down, left, or right, that kind of a thing. All right. So look at your test and make sure you can do it from your test. That's the way to study for this. Okay. Put it in standard form and answer a few basic questions. Okay. Okay. That's basically it. 4 through 6. Given parametric equations. This is still test 1. I would ask some basic questions here. Eliminate the parameter. Find orientation. And possibly a find dy dx, the slope of a tangent line. Okay? Find the slope of a tangent line, and you would do that by dy dt, dx dt kind of thing. Use a chain rule. Of course, you could eliminate the parameter and do dy dx directly as well. Okay, everybody else set on that? Those are from the first test. Now we're into the second test, 7 through 9. I would give you a vector valued function. And I would ask various things, which you would expect. Okay, I would ask for speed, velocity, acceleration, unit tangent, principal unit normal.
What numbers is this? 7 to 9?
Yeah, 7 to 9. Well, obviously, I'm not going to ask all these things because I only have 3 things here. All right, basically, those are possibilities. Now, let's leave it at that, okay? Because those cover everything that's on here. All right, how are we doing? You guys doing all right? Okay. Now, when's your test? Monday? Monday, okay. If that's a problem for anybody, let me know, okay? Because I
Day of
have.
the year.
What's that?
It's the darkest day of the year. I don't know. I'm a little.
Ooh, the darkest. Yeah, it is, isn't it?
Yeah, last day at Calc 3.
Wow, last day of Calc 3. That's what I was thinking
I
of.
guess that's why.
Yeah.
Your darkest day of the year is
The day the doc cam went off.
Why?
Year's exam.
Oh, that's the darkest. Oh. Okay, everybody else set on this?
Almost.
All right, okay, Teddy.
Yeah, I'm good.
All right.
Wait. Sorry.
All right. Set? All right. 7 through 9, and then we've got 10 through 15. Oh my gosh, big section here. Given a function of 2 variables. Oh, find a whole bunch of things. Oh boy. Oh man.
That'll just have to be the drop section.
Yeah. Fine. Things like partial derivatives. Directional derivative. Oh man. Gradient, oh, yikes. A normal vector, what?
What's the du?
This, the directional derivative is what the du thing is, okay? And that's, okay, directional derivative, wow. That's u dot del, u dot the gradient, yeah.
Yeah, I haven't found a gradient in like, I don't even know, at least a couple of days.
Make sure that's a unit vector there. I don't think I can check. Hold on a second. Yeah, I give you a unit
Gradient
vector.
dot the unit vector, right?
Yeah, that's what it is. That's what it is. Normal vector, tangent plane, what? And after all that, a critical value as well? Holy mackerel. So set each of the partials equal to 0 to find the critical value. Wow. And that's that section. 16 through 18.
So the 10 through 15 will be exam 2 is
No, that's 3. Functions of 2 variables.
So if they're not, it's 2, right?
Yes, yes. 16 through 18 is another function of 2 variables, but now we've got a double integral. So, given a function, and I'm going to ask to find the double integral. This is, see, in here, in this one here, that critical value thing, wait a second. Find partial derivatives and all this. Is this 2 separate chapters in here?
It's 3 and 4, I think.
Yeah, I think it's 3 and 4, you're right.
And all the vectors.
3 and 4, because this is 5 right here, the double integral. So that's nothing there. Holy mackerel. They got shortchanged, didn't they? 3 and 4. This is 3 and 4. This is the double integral that gives the volume over a certain region. In the xy plane. Wow, I did that, huh? Wow. Okay, 16 through 18. And you got rectangular in here, but also cylindrical as well, or polar coordinates. Okay, cylindrical, polar coordinates as well, because I give you, there's one with a circular region, and I ask you to do it in cylindrical. So make sure you get that R in there, the R d theta thing. Okay. All right, that's 16 through 18, and then 19 through 22.
So there's 22 problems in this exam?
No, we got a long ways to go. Wow. And then it's 23 to 273, and then 274 to 968. No. There's 25 questions in all. The 19 through 22 is a surface. Okay, so I'm giving you a surface. What the heck am I doing here? Giving a surface and a density function. Find the triple integral. I know it, man. Find the triple integral that gives, it's exactly what you would expect. For volume, you don't have to do them out though. Mass, moment from the xy plane, and that's basically it. And then finally, 23 through 25 is a vector field. Find potential, so it's a conservative vector field. Find the work between 2 points, choose your path, and then work around the square. Kind of a
Will you ask for sections, or can we just use Green's theorem?
it's interesting. I've got potential function, then work done from one point to another, do a linear path or whatever. And then I have work done 0, 0, 1, 0, all right, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, just like we just did. And you can do it any way you want.
So you don't need to show the part.
No, you don't need to show the individual pieces.
We could just use Green's theorem.
You could use Green's theorem. That would be a way to do the problem. What's that? Okay. That would be a way to do the problem. There are other ways to do the problem. So, that is your final. I will now take questions. That's your whole final right there. On Monday, when you take this, I will have your labs, your tests, your WebAssign homework. That's all due 18th. WebAssign is due the 18th, I believe. And then I'll have your final. I'll be able to tell you your grade immediately on Monday. When you leave that room, you will know your grade.
So there won't be like a maximum problem on the exam?
Say that
There
again?
won't be like a maximum problem on the exam?
No. If it's not on what I just told you, if it's not there, it's not on the test. So make sure you can do that stuff.
Wait, so if we didn't do the labs, do any tests get dropped or?
No tests get dropped. If you didn't do any of the labs, that is your drop.
Will
All right.
you be available on email if you have a question?
Yeah, I'm around. I'm a tad behind my emails. I think I'm up to Thanksgiving. I'm up there. I'm pretty current. Yeah, sure. Yeah. Now Monday, 11:15 you take it. So I'll be here Monday. The first exam is on the Monday one is 9:05, I guess. So I'll be here anyways. I'll be here Monday morning, okay, before the
Sweet.
test.
So I can just come in and take it whenever?
Yeah, you could, Teddy. Nobody else can do that, just you. No, you could.
I'll just take it during the time that I'm
Oh,
supposed to.
well, you
I'll
could.
make it easy.
All right, thanks. But I'll be here if you have questions, what I'm saying. Okay, so before the test. All righty? See
I
ya.
can just save all this stuff and just go over it for the,
Oh, yeah, why not? See you guys.
You're still recording.